I introduce now the last two speech, which are focused on tools to support design. And so I invite Mario Caponnetto to take place. These two speeches are focused on the possibility to develop CFD and VPP tools and analysis to support the design in following solutions. That means that over this year, both Mario Caponnetto and Provinciali worked a lot to transfer, to develop, to customize this kind of analysis to adapt to the needs of using following system on different kind of board. They work both for several America's Cup teams, so I think that they have a very updated information to share with us. Yes. Working? Ok, fai tu. Se vuoi. Sì, sì.
So, good morning, everybody. So, as in the title, I would like to speak of the computational fluid dynamic methods that nowadays we have at disposal for foil design. And, but if you can go to the next slide. Before, I would like to talk a little bit of historical background for how we came with the tools that we really have. First sentence, but I think that we have to be very grateful to the engineer that decided to fly airplanes more than 100 years ago, because most of the tools that we have now at disposal in some way have been initially developed to make the airplane to fly. So the same technology that has been developed in aerospace design has been can now be used also for in the marine field, for not also for foil design, but in general for sail design, and we will see later also for hull shape optimization and so on. So we don't really need CFD, computational fluid dynamic, complex fluid dynamic tools to design a wing. We can do very smart simplification and to achieve very good results. So I would say that despite the complexity of a real flow, there are some very smart simplification that really works well to understand how a wing is behaving. So please, next slide. One very clear example. In the left picture, I tried to make a drawing of what looks like the real flow around the two-dimensional foil. So we have streamline, we can see the red on the back of the foil that represent a high-speed flow. That means low speed, low pressure. We have a wake with turbulence and so on. So the flow is normally very complex. But we know that a very smart mathematical simplification of a fundamental equation of the physics works very well to represent the main feature, the principal feature of the flow. For example, we can say that the flow around the two-dimensional foil can be considered as the superimposition of a uniform stream with a vortex. We know this, and it works. This is for two-dimensional foil. If you go to the next slide, we also know that if we have two adjoining foil sections with different intensity of this vortex, there will be a wave shed that is another vortex. See, summing vortices, next slide, please. We can really write a very, very simple mathematical model that can give us, well, maybe I'm a little bit optimistic, say that 90% of information that we really need to make an airplane fly or a foil work can be found using this very simple model. For example, this model has been developed in more than 100 years ago by Lancaster and Grant independently, and it's called lifting line model. I can tell you that it's something that can be solved with a paper and pen or with an Excel file, and it is still used by foil designer as a preliminary tool for the designing the foil. So next slide. Well, we can find very elegant and simple formulation from very basic theory. Well, I put there 3 simple formulas that are valid in general for a symmetric profile and for an elliptical wing. So the lift coefficient, for example, is a constant by the angle of attack for a 2-dimensional foil. If we go to a 3-dimensional wing, the formula changes a little bit, and we have a new variable that is the aspect ratio of the wing. And we have another very simple formula that works under some limitation, but can give us a value of what is called in aeronautic the lift-induced drag. It is a very important part of the drag of the foiling bolt. So next slide, please. So simplified to the maximum with this what we find in this slide, we could really design a first tentative wing. We know the aspect ratio of the wing, the span, the area. We know the relation between angle of attack and lift coefficient. If we go in the literature, we can find some drag coefficient of foil, and we can do a preliminary design of our foil. So next slide, please. Of course, sometimes we need more. And there are many additional information that we want to know that are very difficult to obtain with simple formulation. Because as soon as we want to know more about the flow, the mathematical complexity, the formula, the equation that we have to solve become, I say, exponentially more complex. Okay? So a simple model, very simple. If we want to know a little bit more, we go in a field very, very complicated. Okay? And in the past, still now, but for sure, in the past, the only way to know more about the wing and the flow around the wing was to make a model and to go in the wind tunnel and do experiment of physical models. So next slide, please. The good news is that beside the growing complexity of the information that we want to know, also the computer science has grown exponentially. So we have a computational power now that was unthinkable 20 or 50 years ago. So we can, we switch, or someone before me switched from trying to solve analytical this complex equation that was almost impossible to another approach numerically using the power of a computer. Okay? The big difference is that if we solve the equation analytical, we get formulas that can give us really a good insight in the physics. If we want to use computer, we make mathematical simulation, and the results are not formula but number. Basically, it's a virtual experiment. Okay. Next slide, please. Okay, there are several different ways to solve this more complex problem. There are 2 principal classes of solvers, of a CFD, computational fluid dynamics solver. The simplest one, or the class of the simplest one, is they are called a potential flow solver. The basic simplification is that they neglect the viscosity of the flow, while the more sophisticated tools, solvers, are called in general viscous solver. So again, with potential flow solver, the effect of viscosity is in general neglected in the mathematical formulation, except where it is mandatory to consider the effect of viscosity. Viscous solver, they deal with viscosity, and there are different tools that can handle viscosity in different ways. So please, next slide. So in principle, also the lifting line that I mentioned before is a potential flow solver. So the viscosity is neglected in a fundamental formulation. And the wing or the foil is represented as a line. It's not a wing, but it's a line. If we take a section of this line, this section is a point. Okay? If we want to make the things a little bit more sophisticated and complex, instead of considering the point, the section as a point with a surrounding vortex, we can stretch chordwise this section, this point, and we have the so-called lifting surface formulation. If we want to do another step, we also consider the thickness of the foil, so the third dimension, and we go to what is called now the panel method formulation. So next slide. So you see what looks like the real flow, at least what we can see when the humidity helps us to visualize. We have a wake of vortices, we have a lift distribution along the span of a wing. So on the right corner up, we have the lifting line approximation. So there is a line that represents the wing with many vortices around it, and there are many lines that represent the wake. If we go to another step in the increasing the detail of the flow and of the wing, we go to the lifting surface approximation. So we stretch the line that represents the wing chordwise, and we have different lines that can represent really the 2D section of our profile. And if we consider also the thickness, we go to the panel method formulation. But basically, they are built from the same approximation, but with neglecting the viscosity of the flow. So next slide, please. And I can tell you that the lifting surface and panel method have been really successfully used in the last 30 or more years. And although in the core of the theory, the viscosity is not taken into account, we can solve this ambitious flow, and then we can add a viscous effect in different ways. Okay, for example, adding another simple method that is a thin boundary layer method, coupled with a potential flow. Of course, okay, sorry, next slide. This is how it looks like the panel method visualization. This is a foiling boat. We have a foil, you can see, that is represented with panels on the surface. There are panels on the hull, of course it is in displacement mode. And there are panels that represent the wake that is shed from the foils. If you go to the next slide, again, this kind of method are very useful in a preliminary design phase because they are fast and cheap. What does it mean that they are fast? The computational time is very short, and they are cheap because I can run on a laptop, a very, very inexpensive laptop. Okay. There are another good thing that to solve the flow, I don't need to look at the flow itself, but I simply have to represent and solve the solution at the boundary of the flow. So on the surface of a foil, in the wake, and in the hull. And once we know certain characteristic of the flow on the surface, on the boundary, I can know everything in any point of the fluid. Of course, there is a big limitation that, no, sorry.
Sorry.
Yes. The last sentence. if viscous effects are really important, I cannot use panel codes because panel method results become more and more inaccurate or completely unusable. So if our foil is stalled and the stall is a viscous effect, I cannot use panel codes. So next slide. Okay, all the methods that I presented so far are directly straightforward developed from the aeronautical field. Okay, so I can take a code that has been developed to compute airplane wings, and I can use for foils. But we know that there are some feature in marine foil that don't exist in airplane wings. So one big difference between an airplane and wing is the free surface, because the foil operates at the interface between two fluids, water and air. So, of course, the foil is perturbing this interface, and in general, we will have a production of a wave, spray, ventilation, and of course, we must be able to compute this phenomenon to make a proper design of our foil. Moreover, if a foil is sailing at very high speed, we can have an additional problem or effect, that is the so-called cavitation. So when in some point in the water, the pressure drops below the saturation pressure, the water change phases going from liquid to vapor phase. Okay, and this is another peculiar problem typical of the marine field. Okay, so next slide, please. Okay, so some kind of free surface problem can be computed with panel codes. So if we have a smooth, regular wave, like in a foiler when it's not foiling, panel codes can handle this problem very well. Okay. Next slide, please. We can do cavitation analysis also with panel codes. In this example, I've been working with propeller design for many years and developing panel codes for cavitation computation. So this is a case with of the cavitating propellers, and you can see the comparison between the cavity observed in the cavitation tunnel and the one computed with a panel payload. The same code, of course, can be applied also for a foiling boat. Next slide. But these are quite rough approximation of a real flow. So to properly capture all these free surface and cavitation phenomena all together, we need a more sophisticated codes. And what made possible to make a big step has been the introduction of a volume of fluid solver or similar methods, let's say more or less 20 years ago. And both methods can really handle extremely complex free surface feature, spray, overturning waves, ventilation, and cavitation. Next slide. So this is an example. I try to push this foil to make more spray, of course. But you can see that this is a volume of fluid computation of a typical foil. And we can see that we can capture the spray. You can see a red line along the leading edge of the strap. That is the visualization of a cavitation. So there is vapor pressure inside that rocket. We can handle also the spray of the tip, but we can handle also the waves generated by the foil. Everything together. Next slide, please. Okay, and we can get a lot of information. And maybe we can go forward. These are the tools that we are normally using to design foils. And again, this is not a kind of computation. These are crosscuts of the free surface, starting from a section at the foil location, when you see how the water is rising from one side and going down to the other side, and downward cut where you see how the free surface is really contorted, generating, entrapping air and so on. This level of information can be achieved only with the tools, high-end tools like volume of fluid solver. Next slide. Well, I want to show you how we can, this is the typical path from the concept of the foil to the computation. So what we normally do is, of course, basing on idea experience, to generate a new CAD geometry. Then we want to do the computation. So there are three separate processes. The first process is called the pre-processing, that basically is to mesh, to model numerically the geometry. In this case, if this is not a panel code, we had to put panels or cells not only at the boundary of our domain, but also inside the domain. The number of elements of cells rise enormously, so normally we can do computation with 10, 100 or more million elements. That means to solve a system of equation with million and million of variables. We cannot do this on a laptop normally, so we have to do with quite powerful parallel computation. So we need a cluster of processors that are working in parallel, each processor doing computation on a specific part of the domain. Okay, so you can go over. So to finish, there is an almost general consensus, at least from CFD user point of view, that sophisticated CFD solver can give a result equivalent in precision with some wind tunnel experiment for typical computation, production computation. There are pros and cons with both methods, experimental and CFD. Next slide. Basically summarize, CFD normally is faster, cheaper, and allow easy flow visualization, better flow inside. We can look at the flow much better than or easier than in a wind tunnel. We can control the boundary condition, the ambient condition, that sometimes are difficult to control in a towing tank or in wind tunnel, and we can do much more. Of course, we need a user that knows how to do, but also in a wind tunnel it's the same. And for sure, the physics is not perfectly reproducible. But, okay, we go to the next slide. One more sentence. That the way we normally use CFD until now has been to virtually replicate an experiment. So we have a benchmark experiment. We wanted to be sure that the CFD code is able to replicate it. So we tested like a virtual towing tank, like a virtual wind tunnel. And there are a lot of limitations in the experiment. In experiment, we had to fix the model that is constrained into a balance and so on. Now that we know that the CFD tools are accurate enough, we can use CFD in a more clever way. So we don't have to simulate only steady condition, but we can simulate unsteady condition, maneuvering. We can consider the geometry, the foil in this case, as the formal, and so on. And we can do exactly the same as in the past, so to collect all the forces, hydro force, and put in a VPP, or next slide. We can do a global simulation. We can compute water and air all together. So simulate the boat with the sail, the wind, and everything, and cavitation, and do a global computation, but at this stage is more a double check that the VPP is doing things properly. And we can also couple CFD with finite element method to see the deformation and the stress of a foil under hydrodynamic load. This is something that will be extremely complicated to do in experiment with experimental tools. So next slide is the last, I think. Okay. So, well, of course, there is a lot of development to do, and I think that there are a lot of merit in using CFD now. And thank you. Thank you.